This is Chemical Processes for Micro and Nanofabrication. I'm Chris Mack, your professor for this UT Austin course, and we're at lecture 50. It's hard to believe we've made it to 50 lectures already. This lecture is on lithography. We've been doing quite a few on this topic. We've switched now from the optics of lithography to the chemistry of lithography, and today we're going to talk about the photoresist ABCs. As we saw last time, the exposure kinetics for all of the resists that we use in semiconductor manufacturing today, is first order. That is, the rate at which the sensitizer, the light-sensitive component in the resist, disappears with time is proportional to its concentration to the first power. It's also proportional to the intensity to the first power, and the rate constant, the constant of proportionality, is C, which we call the exposure rate constant. If the intensity is constant with time, we can integrate this equation and find a relative sensitizer concentration, little m, equal to e to the minus CIT. C is the exposure rate constant, as we've said, and I times T is the exposure dose, or the exposure energy. What we're going to find out today is that for some classes of photoresist, I is not constant with time, and we have to understand that variation of I with time if we want to be able to solve this rate equation. And to start with our understanding of how the intensity inside the resist varies with time, we need to start with a description of absorption. And the fundamental principle of absorption is called the Lambert Law of Absorption. It's a very well-established law. There are some materials, especially at extremely high intensities, where the Lambert Law of Absorption is not seen to be true, but that never happens in the materials that we're dealing with. Lambert absorption law is going to be perfectly valid. It says, as an intensity I, as light travels through some material, the intensity I varies with depth into that material in a way that is proportional to the intensity. The proportionality constant is called alpha, the absorption coefficient of the material. So this is the Lambert Law of Absorption. The relative change, or the fractional change in intensity, di over I, is a constant over a unit length, dz. Well, if this absorption coefficient alpha is constant, we can simply integrate this equation to obtain a very common and very well-known absorption law. I, the intensity as a function of depth into the resist, equals the intensity at the top of the resist, E at z equals 0, that would be the top, times e to the minus alpha z. This law, or this equation rather, is often described as the Lambert Law of Absorption, but it's not. The differential equation is the Lambert Law of Absorption, and this is the solution to the Lambert Law for the special case of alpha equals a constant. We're going to find out that for some classes of photoresists that we use, alpha is not constant. It varies as a function of depth into the resist, and therefore we cannot integrate this equation and obtain e to the minus alpha z as our absorption variation. So let's look at the coupled ideas that intensity is not constant with time and alpha is not constant with z. And to do that, we will invoke another law of absorption called Beer's law. But before I do that, though, let me mention one aside topic. This is an interesting topic. We're not going to really explore it in this class, but it is commonly, it's a common little tool that we use in optics. We can relate alpha, the absorption coefficient, to kappa, which is the imaginary part of the refractive index of the photoresist. Alpha is 4 pi kappa over the wavelength, lambda. What this means is we can take the conventional refractive index of the photoresist that we've talked about in our discussion of optics and extend it, call that the real part, and then add to it this imaginary part, and create a complex refractive index of our material. And the complex refractive index accounts for both refraction, the bending of light as it travels from one media to another, and absorption. And it's the imaginary part of the refractive index that accounts for absorption. We see this very, very commonly done in the world of optics. It's a great little tool, a little technique that we use. But we're not really going to be talking any more about that in this course. Just wanted you to be aware of it. But now let's look at another law of absorption. This one is called Beer's law. Beer's law is also an empirical law, like the Lambert law, but unlike the Lambert law, which has very, very few exceptions, Beer's law has many exceptions. In fact, almost every material disobeys Beer's law over some range. And that's going to be the key. There'll be some range over which Beer's law is useful, and other ranges where it's not, and you have to empirically determine whether Beer's law is applicable in your situation. Well, what is Beer's law? Beer's law simply says the absorption coefficient alpha is proportional to the concentration of the absorbing species. So, if I have one molecule of absorbing species, I get a certain rate at which photons are absorbed. If I have two molecules of the absorbing species, I double the rate at which, double the probability that I'll absorb a photon, which essentially doubles the rate at which photons are absorbed. If I have four molecules instead of two, I again double the probability that a photon will be absorbed. And so alpha goes up in proportion to the concentration. So the proportionality constant we call the molar absorptivity of the material that's doing the absorbing, and Ci is the concentration of that material. The Beer's law always fails at high concentrations. In other words, the idea that if I double the number of molecules that can absorb, I double the probability of absorption, rests on the assumption that the two molecules are independent of each other. That is, the ability of one molecule to absorb a photon is independent of the presence or absence of another molecule nearby. That's true as long as the molecules are far apart. When they're far apart, they don't influence each other at all. So adding more molecules simply increases the probability of photon absorption. But once the molecules get very close to each other, then that's no longer true. The ability of this molecule to absorb a photon becomes influenced by whether or not I've got a molecule close by. In quantum mechanics, we say that the wave functions begin to overlap, and as a result, these probabilities, the energies, and therefore the probabilities for absorption begin to change. We don't need to worry about the details of that, but the lesson is at high concentrations we get deviations from this linear relationship between absorption coefficient and concentration. And we need to empirically find out where that high concentration limit is. We'll talk about that for photoresist in a moment. If I have more than one absorbing material, I can use this independence argument that each molecule is absorbing independently of all the others, as long as the concentrations are not too high. And I can say the absorption coefficient alpha is the sum of A times C for all of the absorbing components. If we apply this Beer's law, multi-component Beer's law, to our photoresist, we end up with an equation that looks something like this. What do we have inside of our photoresist? Well, we've got a sensitizer. Well, that's M. So I'd say one piece that absorbs is M, and it has a molar absorptivity of A sub M. Once I start exposing, I also get exposed sensitizer, the product of the exposure reaction. I call that P, and so we have A sub P times P, which can also absorb light. Other things in the resist can absorb light. The resin, Novolac resin, or other polymers that might be in the photoresist. We have solvent, even though we've coated and baked our resist already, there's still some residual solvent left that could absorb. And we have other possible additives in the photoresist, each of which could absorb. So we just keep adding more and more components. That's Beer's law. If we want to use it, we have to empirically validate it, mixing up resists with different amounts of these components and making sure that this linear relationship applies. That has been done. I personally performed those experiments and showed that for the resist we're going to use this for most is DNQ Novolac resists, and over the useful range of DNQ concentrations, Beer's law holds. All right, so Beer's law can be applied to our photoresist, but when I look at this, I notice something interesting. Some of these concentrations are exposure dose dependent. Once I begin exposing, M goes away and P starts being formed. So if the molar absorptivity of the sensitizer is different than the molar absorptivity of the product, I will see a change in alpha, the absorption coefficient. I can clarify that by lumping together exposure-dependent terms with exposure-independent terms. So if I do that, I can express alpha as AM plus B. M is the relative sensitizer concentration, and A is going to be this collection of terms. It's the difference between the molar absorptivity of the sensitizer and the molar absorptivity of the reaction product P. That difference multiplied by the initial concentration of the sensitizer. B, on the other hand, will be this collection of terms, and you see all of the terms that do not change with exposure. As a result, we call A the bleachable absorption coefficient and B the non-bleachable absorption coefficient. What do I mean by that? Suppose that A is positive. Now, what's the initial value of M? Little m is the relative sensitizer concentration, and at the beginning of exposure, little m equals 1. All of the DNQ is there when I start my exposure. Then I begin exposing and M goes down. Sensitizer begins to disappear. And what's the final value of M? Well, if I were to expose out to infinity, the final value of M would be 0. So the absorption coefficient alpha starts out as A plus B, and as exposure proceeds, the AM term disappears and alpha goes down to just B. So if A is a positive number, then alpha begins as a larger value, A plus B, and then decreases to a smaller value, B, during exposure. We say that the photoresist bleaches, that is, it becomes more transparent. Bleach removes color. So without the color, it becomes transparent, and alpha decreases from the beginning to the end of exposure. That's why we call A the bleachable absorption coefficient. One consequence of this behavior is that we cannot assume the intensity is constant with time or constant with depth into the photoresist. So here's our first order kinetics. I've rewritten it in terms of little m instead of big M, but it's the same equation. And I might say I'd like to integrate this by putting the dt over here and the m down here, but if I is not constant with time, I can't just directly integrate this. And I will not be constant with time. Why? Because the photoresist will begin to bleach. It will become more transparent, and as a result, more light will make it to the bottom at the end of exposure compared to the beginning of exposure. The intensity of light inside the resist will change with time. Likewise, with bleaching, I'll have more bleaching at the top of the resist than the bottom because it has higher light intensity. With more bleaching at the top, my absorption coefficient at the top of the resist will be less than at the bottom, and the Lambert Law of Absorption, which I've rewritten here, cannot be solved assuming the absorption coefficient is constant, because it's not. The absorption coefficient is AM plus B, and M varies with depth. Why? Because I varies with depth, and M varies with I. In other words, I have two coupled first-order differential equations. This is why I've rewritten them with partial derivatives, right? Because this shows the partial derivative of m with time, and this shows the partial derivative of I with z. In reality, I and m are varying both with z and time, and we need to solve these equations, these coupled partial differential equations, simultaneously. Well, that's a little bit of a hassle. Other than for some special cases, we have to do those calculations numerically, but they're not that hard once we're used to those kinds of numerical calculations. We won't do them in class, but know that they're not particularly hard to do if we needed to. Notice that we have three parameters here that describe the coupled behavior of both exposure and absorption. C, the exposure rate constant, and A, the bleachable absorption coefficient, and B, the non-bleachable absorption coefficient. These three parameters for a photoresist are called the ABC parameters. Thus the title for this lecture. They're also called the Dill parameters after Rick Dill, the IBM researcher who first came up with this model and named these coefficients the ABC parameters back in the 70s. So, how do we measure the Dill ABC parameters? Turns out that they can be, in some circumstances, very easy to measure with a laboratory equipment that most anybody could build. You need a light source at the wavelength of interest. So I consider, say, a mercury arc lamp, a collimating lens, and a bandpass filter to create light in one wavelength, and also light that hits the photoresist in one direction. I want normally incident light. Then I take my photoresist, and instead of coating it on a silicon wafer, I coat it on a glass substrate, a transparent substrate, transparent at the wavelength of my measurement. I will also try to make the substrate, the glass substrate, optically matched to the photoresist. That is, I want them to have the same refractive index, the same real part of the refractive index, so that I don't see any reflections between the resist and the substrate. That is, I can assume all the light transfers straight through. Now, I don't actually have to be that perfect about it. I can account for any stray reflections, just makes the analysis of the data a little bit more difficult. Then I have a light meter that collects that light as a function of time, and the result, transmittance versus time. Or, knowing the intensity, transmittance versus dose. Kind of common curve that might result from this measurement is this transmittance versus dose curve. There are three important regions to this curve. The initial transmittance, I label it T of 0 over here. The final transmittance, I get to a large enough energy that this flattens out and reaches a plateau, the infinite dose transmittance. And then finally the slope of this curve, dt, d energy, dt, de. And especially the slope initially, the initial slope. From this curve I can extract all three parameters, A, B, and C. A and B are as follows. A is 1 over the thickness of the resist times the log of the infinite transmittance divided by the initial transmittance. Now, the log of the ratio is like the difference, and so the bleachable absorption coefficient describes the difference between how much is transmitted and as a result how much is absorbed initially versus how much is being absorbed at the end. B, on the other hand, tells us about how much is being absorbed at the end. This is the non-bleachable absorbance. And B is minus 1 over D times the log of the transmittance at infinity relative to the transmittance of the air resist interface. So some light is reflected off of the air resist interface when it first comes. What I want to know is not how much is reflected, but how much is transmitted that actually gets into the resist. So I kind of normalize by dividing by this air resist interface transmittance, which we can calculate based on the refractive index of the photoresist, that's N2, and the refractive index of the air, which is N1. So that's what these N2 and N1s are. The real part of the refractive index of the photoresist and of the air. So 1 represents air and 2 represents photoresist in this numbering scheme. Then I can calculate the value of C using the slope, in particular the slope dt dE at E equals 0, at 0 dose. That is the initial slope of this curve. From the initial slope of this curve and these other parameters, I can extract the value of C, the exposure rate constant. Of course, we don't have to do this graphically. The best approach is to fit the whole curve, the measured T of E curve, with a numerical solution to our coupled first-order partial differential kinetic equations. The Lambert Law of Absorption combined with Beer's Law and the first-order kinetics equation. We simply numerically integrate and calculate T of E and find the values of A, B, and C that provide a best fit. Note that if A equals 0, we have a resist that does not bleach. That means the absorption coefficient alpha will remain constant as a function of exposure dose. In that case, well, A is 0, B is still something we can measure, but C cannot be measured in this way. We have no way of seeing what rate of exposure is occurring. In other words, when we have a photoresist that bleaches, we can use the bleaching property as a way of probing the exposure reaction. We can extract the kinetics of exposure because the resist bleaches, but if A is 0, then we need some other technique to measure C. The Dill ABC parameters are also a function of wavelength, especially in the case of G-line and I-line photoresists, and even broadband exposures where we use a range of wavelengths to expose their photoresist. We would like to know A and B as a function of wavelength, and we can obtain that with a UV spectrophotometer. Here's an example for a G-line resist where B is relatively small for the wavelengths of exposure of interest for this G-line resist, and A is high, meaning that we are getting a lot of bleaching. For an I-line resist, we probably want B to be lower. So out here at about 365, we would adjust our photoresist to have a somewhat lower B value to get better performance for an I-line resist. But it wouldn't be that much different than this behavior. Here are some typical ABC values for G-line resists. Remember, G-line is 436 nanometers wavelength. We see A something like 0.6 inverse microns. A and B have units of absorption coefficient, which are units of inverse length. And C is something like 0.015 with units of inverse dose, centimeters squared per millijoule. Typical kinds of values. B is usually reasonably small, 0.05 for example. For an I-line resist, we find that A is a bit bigger, 0.9, and C tends to be a bit bigger as well, but still on the same order of values. When we get to 248 resists, chemically amplified resists, we find that these resists do not bleach. They have A values of about 0. Some of them actually have a negative A value, small negative A value, which means the photoresist darkens upon exposure. But usually the darkening is so slight that we don't have to worry about it. A is about 0. B, on the other hand, is much higher. Total absorption is not higher than the previous resist, but it's just that most of the absorption does not result in bleaching. So B is higher, say about 0.5. And C is higher as well, something like 0.05 centimeters squared per millijoule. The higher value of C is reflected in the higher amount of energy in each photon. That comes with the lower wavelength. And for 193 resists, we also see that A is 0 for these resists. So 248 and 193 resists are non-bleaching resists. B is higher. It's a 193 resists tend to be more absorbing, and we compensate for that by using thinner resists. And finally, we can modify the B value by adding an absorbing dye. As we saw when we talked about standing waves and swing curves, it is occasionally useful to add dye to the photoresist in order to suppress the standing waves a bit and to suppress the swing curves. And we can easily increase the B value into the 0.3 or 0.5 range, generally for G-line and I-line resists, because we only want to dye resists when we are not using a bottom anti-reflective coating. For 248 nanometer and 193 nanometer lithography, we almost always use a bottom anti-reflective coating, so we have no reason to increase the B value. And finally, I will mention that this macroscopic view of absorption and exposure can also be described on the microscopic scale. How does an exposure of one molecule occur? Well, the exposure rate constant C is going to be proportional to, first, phi, the quantum yield. That's the probability that an absorbed photon will lead to an acid. Sometimes you absorb a photon and the absorbed energy is dissipated in other ways. So the quantum yield is less than 1. Not every absorbed photon leads to a chemical reaction. Then we multiply that by the absorption cross-section, which is basically what's the probability that you'll get an absorption by the sensitizer. An absorption that has the possibility of leading to a reaction. If the light is absorbed by a non-reactive species, I'm kind of wasting that light. So here the absorption cross-section is only for the reactive species. And finally, we have this hc over lambda term. H is Planck's constant, c is the speed of light in vacuum, and lambda is the vacuum wavelength. Hc over lambda is the energy of a single photon. So, let's review what we've learned about the ABC parameters and how it relates to exposure kinetics. We saw that absorption and exposure together are described by these three parameters, A, B, and C, called the Dill parameters, or the ABC parameters. One of those parameters is C, and it's the exposure rate constant that comes from our first order kinetics of exposure. Positive values of A means the photoresist bleaches upon exposure. And we found that for G and I line resists, the DNQ Novolac resists, we have fairly large values of A. This is actually a good thing. It helps with the photoresist. But for 248 and 193 resists, we have A values of 0. B can be increased by adding an absorbing dye. So what have we learned? As always, you should be able to quickly and easily answer these questions. If not, go back and review the material. What are the ABC parameters? How can one increase the value of B? How are the ABC parameters typically measured? What are typical values of A, specifically A, you should know this, for 248 and 193 nanometer resists?